Alright, so this was the syllabus. So if you consider the first module, that's what we have discussed so far about the introduction, the security service and the classical encryption techniques. Now the second module is mathematical foundation, in which we are going to discuss certain topics which has been listed there, but it's a broad generalization that has been mentioned in the module. So we will focus on specific I would say operators and operations which will be useful in leading to the third and the fourth module, in which few of the operations you already we are aware of. For example, the modular operator, the divisibility, the multiplicative inverse calculation. So those things we have already done, or at least have used in certain aspects. So now in this particular module we will go up to a certain extent. I think till the Chinese remainder theorem, I think that will be the syllabus. Up to that portion we can finish off within these 5 days, if not the whole. But at least that will be the syllabus for your CAT 1. Alright, the first module and the portion of CAT module 2, but that depends on how much we are able to finish. Alright, so based on that we will decide. So like that aspect, so we will go directly to the second module and let's start. So basically these are the outlines of the second module which we are going to discuss. Alright, so this is basically the detailed syllabus of the segment. So we'll start with number theory and finite field. This itself, I would say, to be honest with you, this will become a little boring because it's more like an abstract mathematics. So in some cases we will opt out of going into further details of it, because this is not a mathematics class. As I said, we are going to focus on areas which will be useful for our second, the third and the fourth module. So the application area is where we are going to focus more on. Okay. So if you already know a few of these stuff, you might find it a little boring in that way. For example, the Euclidean geometry or the Euclidean algorithms, you will find that the process is very much known to us, but we have to follow those algorithms for future purpose. So that's why we have to go through those rigorous calculation part of it. So keeping that in mind, alright. So this is the first element. So you can see the number theory and finite field. So this is our discussion for the time being, under which we have this many subtopics which we are going to discuss. Again, this is not there in the directly given in the module in the syllabus for that matter. But at least these are the elements which we will require at some point of time. So that's why we are going to discuss. It's not limited to this element. There are many other elements which are there. But at least this many groups, field, polynomial arithmetic and all those things will be required at some point later. So that's why we are going to discuss, or at least brush up our knowledge on it. Okay, just like we have done the previous few things. Alright. So the integer arithmetic is very common to you. I think we are not going to discuss much on this. So we use a set of few operations. Specifically, if you observe that the topics discussed in this section, in that we have set of integers. So now integers will play a very important role, because based on these integers and how we are arranging those integers, we will classify them into groups, we will classify them into fields which are some specific terminology associated with it. Okay? And remember, all these operations is useful for cryptographic algorithms specifically. That's why we are going to have a discussion. Similarly, we have integer division, divisibility and Euclidian algorithm. So that's what we are going to discuss one after another. I'll see to it that as much as easily I can go through this part, so that you are not in a position to have any boredom on this. So first is that integer arithmetic deals with infinite number of numbers, which starts with negative minus infinity to plus infinity. So if we denote that as z, okay, so this z is a very common nomenclature for cryptography as well as for all the operations that we come across. So please, just like we had done for P and C for plain text and cipher text as the common terminology for plain text and cipher text, so please make a note that z indicates the collection of all the integer numbers. This is a common terminology used all throughout the discussion. So later on we are not going to discuss, again coming back, so please refer to that. Z indicates that. And in cryptography we are interested in 3 basic binary operations, and that's very important. Now this binary operation is a term which will be coming handy when we discuss about the group and field, which is coming later. For the time being, we will only assume that the plus, minus and multiplication, these are the three operations that we have to take into account whenever we are looking at a set of integers working for cryptography. So if you observe that what is a binary operation, it basically indicates that we will consider two input and we will get an output which is 1. So you can observe that this z we are looking at minus infinity to plus infinity. We apply the any two element a and b, you can see here a and b, and we operate on plus, minus and multiplication, and we get another set over here which again is a product of the operation that we come across. You will soon find that these operators, the binary operator, now see it is as it is a discrete mathematics, we will not specifically call this as the plus, minus or multiplication. At some point we are going to use this term as the binary operator, okay, and that will be used for groups. Again, as I said, we will come to that later. But if you observe carefully, here the division is not considered over here. The division operator is not considered over here for a specific reason, because if you do it a division, we usually come across two outputs. One is the quotient and the other one is the remainder. So that is taken care of by the modular operator and it is separated out from the binary operation itself. So usually the binary operators are plus, minus and multiplication. Okay, so that's what is being mentioned over here. Now following the results, as I can observe that this is some of the very preliminary examples that we come across, that for addition, subtraction and multiplication you can observe that the product of all this operation will be another element which will be part of the set or the part of the integer set that we have considered. So that's pretty obvious. In fact, based on that we will assign certain rules and regulations on the data set for that matter. Okay, so this is just an example of it. Next it is the division part. Okay, so now this part is, as I said, we have already discussed quite a few examples, especially while dealing with the classical encryption techniques, where you will observe that most of the encryption as well as the decryption operation, we have utilized the option of divisibility, and in order to do that we have the formula A equals to Qn plus R, where, as I said again, that R is the factor that we are mostly bothered with, R, okay, the remainder part. But you will soon find that the Q will also play an important role as we discuss about the Euclidean algorithm for that matter. Okay? So this is one of the examples of it, just a briefing of it. Now, in that aspect, let us see a little bit on the minus, the negative integers, that how we can consider and how do we go about doing it. So if you consider over here that whenever we use a computer or a calculator, R and Q are negative when A is negative. Alright, so if the number is negative itself, naturally my outputs will be negative. So negative in any way, we have to make it positive. Remember in some of the examples we did that. Now the rule for this is very simple. It is or not always that we have to add up to that of the quotient. It's not always, rather we usually add up the modular operator with the remainder of it, right? So that's the same thing here we are doing. But the algorithm or the rule for this is, if you observe the example, the solution is simple. We decrement the value of Q by 1 and we add the value of N to R to make it positive. Just for example, we have given here minus 255. Now minus 255, if you divide that by 11, suppose modulo 11 is there, minus 255 mod 11. So in that case, you are getting minus 23 as the quotient and minus 2 as the remainder, right? Now the rule is that you have to increase the quotient by 1. So you can see the right hand side, we have increased that to minus 1. So adding up in that way, we will have minus 24. And we add that 11, you see that modulo 11 is there. So 11 minus 2 we are doing. So basically what we are trying to do, please make a note of it because it will be useful sometime later. So this is my quotient, this is my modulo operator and this is my R. Now what the rule is, Q is taken minus 1. So it is like, as it is negative, so we are adding up minus 1. So now Q has become minus 24 for that matter. And why this is 9? Because we have made 11 minus 2. Because minus 2 was the remainder. So we have made 11 minus 2 over here. And that's why we have made it plus. And the remainder is now as plus. Same you can see that the bottom example, 5 minus 512. So you have minus 2 over here. Same way 10 minus 2, 8 has been considered over here. And this quotient has increased to minus 52. We will find that in subsequent slides when we come across, especially with the Euclidean algorithm, we will come across this negative terminology. So the same logic should be applied there. It might be that the number will be pretty high, pretty long. So in that case, it's very difficult to find out the way, if you are not doing it the way I am doing over here, it will be really difficult to solve out at some point. So please make a note of it. So whenever we have a negative value of A and we are getting the quotient, the remainder as negative, then the rule is that we have to make the quotient to be minus 1, like increase by 1, and we have to subtract the remainder in the original case from the modular operator or the A. Okay, so that's the rule, and we make it possible. So that's one of the example and the applications of it. So this is about the another aspect to understand. Achha. Now this is again very common, again the divisibility when r is equal to 0, when we don't have a remainder, naturally our equation will be q into n, but you can see the operator, how it is represented. It's not that generic way of representation. If you observe carefully over here, okay, so this is the way it is represented, a divided by n. So this is the how it is represented, okay. And if it is, if the remainder is not 0, it is usually this operator is used. Alright, it is not very commonly used. This is not being used, the operator that we know of. Alright, so because it's a remainder modular operator, so we have to use that way of it. You can see the integer 4 divides integer 32, we know, but the process of representation is 4 divided by 32. So 32 divided by 4, but it is represented in that way. Okay, so in your given numerical, sometimes if you get across 4 divided by 32, it means the meaning is 32 divided by 4 in that. Okay. So that's the difference. Even you can see 42 here is not divisible, so you are taking this cross. Okay, so that's how it is represented. Yeah. Previously. This can be anything. This is just a division we are doing. This is modulo 11 actually. Here the question is 255 mod of 11 actually. So that's what we are doing. I'm not mentioning that. So basically you are dividing by 11, so you get the quotient and the remainder. If they are negative, you have to use that process. That's it. In this case, actually it is like minus 512 mod 10. It's like this. So that's how. So this is about the divisibility. Now these are the properties. Please make a note of these properties. It will be useful sometime later. First property is one divisible by a, and then it is naturally a is equal to plus minus 1. So please make a note of these rules. Next one is if a divided by, or rather b divided by a, in that way the divisible operator, or a divided by b, then a must be equal to plus minus b. These are just generic some rules you need to know later on when we come across any such operation. You should apply these rules. Otherwise, because it is not that a and b will be 4, 5 like that. It might be very huge number. At that time, those rules will be very useful in throttling the time. Right? So that is the advantage of it. So if a and b like this, you can mention that. Third property, if a and b is divisible like this, and b c divided by b, then a should also, like c should also be divided by a. You can see, observe that at the bottom I have given some of the examples. The first one you can see that we have 78 divided by 13, alright, 98 divided by 7, alright, 24 divided by minus 6, 44 divided by 4. So all these cases you can observe that they are all following the rule, alright. And you can see the next one also is like indicating that it's not, they have a remainder and all. Third one, if you observe the third line that you observe, that 15 divided by 3, and if it is 45 divided by 15, alright, so it is applicable the third one actually, property third. So then we have 45 divided by 3 is also a proper divisible element. Okay, so similarly you can prove the other laws also. You can prove, you can take any example and you can just go on proving it. It's just that it's not about the proving it, It's just about application of it. So that's the main purpose of it. The last one also you can see that if A divided by B, or in that way if I call it, and if A is divided by or C is divided by A, then we can write M and N as two arbitrary integers over here, which will make the third equation to be satisfied. M cross B plus N cross C will be divisible by A. So you can see the last example that I have taken over here. The last example that I have taken over here is actually the application of the C. Okay, here 2 and 4 applicate is the B and C, or rather M and C, M and N, and you have 15 and 9 as the B and C. So you can see that the 66 divided by 3, that one also is following the rule. So it's just the application, nothing to worry. It's just usage of the properties. Just keep a note of these properties. Sometimes you might use it. Okay. Right. Now again the same thing. Again see, GCD I should not be explaining to you what is GCD and all. But as I said, the GCD, it is not about only 60, 10 you find the GCD of it. It's not like that. We will always come across huge numbers, and that huge numbers requires GCD. Now if you go on doing it in the normal conventional way, it will take a lot of time. That's where the Euclidean algorithm will come in to follow, to find out what is the common divisor with respect to those numbers. So in general way, it's what is the largest integer between the two. So this is the example of it. The two things that you can see, fact 1 and 2, that's what you have to understand. One is the integer 1 has only one divisor itself, and second, any positive integer has at least two divisions. 1 and itself, one more. So this is just a pictorial description of 12 and 140. But see the difference, how it goes. Alright, so this is about the algorithm. This is the first of the algorithm in finding out the GCD. This is with respect to smaller integer values. So if you observe here, GCD equals to A comma 0, if it is, then definitely the GCD, the value is A. So please make a note of it. And the next one is A comma B, if it is. Now A and B, if suppose we are imagining, not for the small numbers, if they are arbitrary big numbers. So in that case, if it is equal to GCD, it can be mentioned as GCD B comma R. See, this B and B is repeating. So if suppose you have that scenario where A and B are high, huge numbers, we'll see an example, then we can equate that to GCD B comma R, where R is the remainder of A divided by B, divided by A by B. So that forms an algorithm. That's from the first of the GCD algorithms, which we actually have discussed a little bit while discussing the algorithms previously in the module 1. So this is just an example of it. For example, GCD 36, 10. Normally we don't have any problems. Just like we can do it, go on doing it and finding out the GCD, not a problem. But if I follow the trend of the equations for that matter, so if you see this is my A, this is my B, so we can write that as B comma R over here. Why R is 6? Because the remainder of 36 divided by 10. Okay, so that's how we are doing. So remainder is coming as 6. Similarly, this becomes A and B for the next step, for which the GCD becomes 6, 4. This is going internally, how it is being processed. That's the algorithm we are talking about. Finally, we are getting 2 as the answer. But as I said, this is we are very much aware of it, how we can find it out. But for longer values, for a bigger number, which might be the case for most of the cryptographic algorithms, we are not going to deal with so small numbers. When we have a huge number, large numbers, we need to follow the algorithms of Euclidean algorithms to find out the GCD. Okay, so let's see how it is to be done. This is ideally the algorithms that we have discussed right now itself. You can see that R1 is A and R2 is B. Remember, we had discussed a very similar thing when we discussed about the multiplicative inverse as well. Now, when R2 is greater than 0, what will happen? Eventually, the remainder will be R1 minus Q R2, and R1 will be replaced by R2 value, and there will be a shifting from R to R2. Now, in this context, you can see the algorithm is 2000 years old, but still it is relevant, especially given the fact when we are dealing again, as I said, with the larger numbers, it is still relevant to use this formula and the algorithm. Okay. And as you can see, the GCD, if it is 1, A and A comma B 1, please make a note of that last line, because you will find that there are two algorithms, Ferret and Euler's theorem, which you will come across in this module itself. They are going to deal with the prime numbers and the relative prime numbers. So there also we will refer, or somewhere down the line, one of the conditions we are going to refer as GCD comma 1. That's kind of a testing scenario. Remember, in multiplicative inverse also, I told you that this is a multiplicative inverse only exists if GCD of A comma B equals to 1. So always somewhere down the line this will be a relevant equation or relevant condition at some point. So you can see that if GCD equal to A comma B is equal to 1, then we say that A and B are relatively prime. Relatively prime and its properties we will discuss when we discuss about the Fermat's and Euler's theorem later. Alright, so just an example over here. So keeping that in mind, for example, this is one of the examples where you have a relatively large number for which you have to find the GCD. Alright, so this is only one of the examples. You will soon find the example will be even more. So the rule is very simple. As you can see that we have arranged it in terms of R1 and R2. Simple as that. And we are making a division over here. So the quotient over here is 1 and the remainder is 980. Now as per the rule, 1760 comes over here, 980 comes over here. Alright. And we again find out what is the quotient and what is the remainder. Like that we will go on doing it, shifting and updating the variables. Finally, whenever we get across R2 equal to 0, if you remember the algorithm back then, R2 should be greater than 0, right? This is where we have discussed the while statement, while R2 is greater than 0. So after a certain period, when R2 will become 0, then whatever be the output of R1, that will be considered as the GCD. Right? So this is the process. Now in your exams also, we are going to give you some very big numbers for which you have to apply the rule and show us the step or the tabular approach to give me the final answer. Alright. So let me just give you that, maybe this one. Can you find me the table and give me the final answer of the GCD using the formula or the algorithm that I considered, and find the GCD using the Euclidean algorithm to find out the GCD for these two given number 1160718174 and 31625825. Please do it and tell me. That is what I was telling you, that whenever we come across huge numbers, this is just an example. Similarly, we will get across many huge numbers in cryptographic algorithms. Especially the numbers are important because the more the bigger number, the more the chance of making it secure. The smaller number can be deciphered easily, so that's why we will make it longer. Okay, even in communication also it happens the same way. Okay, we will change only single bit amongst all the other bits, so that makes things really difficult for detection purpose. So suppose we have a scenario like this and we want to use it some way, the GCD of it. So how we are going to do it? So please follow the table. Okay, I'll give you the table here. I'll just for a reference I'll give this table to you so that you can have an arrangement. First you write the Q, then you have R1, you have R2 and you have R. So find me the tabular approach to get the answer for the equation given. Take your time, but please do it properly. Done? So if you observe, this is the complete list of solutions for this particular example, and in that way you will go on doing it. This is just not the tabular part. You can see R9. Okay, if you observe there, so that's basically why we are getting around 1078. Okay, so or rather the remainder is 0. So in that way we are going to get it. So the point is that if I get a very huge number, we have to follow the process involved with the Euclidean algorithm and find it out. Now the point is, we might also need the GCD A comma B to be represented in a form S multiplied by A plus T multiplied by B. Again, it is, as I said, they are part of the different sets of algorithms where we might use this form. So you can see that given two integers A comma B, we often need to find other two integers S comma T from the GCD value itself. Now how we are going to do it, that's also, this is called as extended Euclidean algorithm. So please make a note, S multiplied by A plus T multiplied by B, where A and B are the GCD element of GCD of AB. Now the extended Euclidean algorithm suggests that there can be additional two columns of S and T, which will again go on updating itself, very similar to how the remainder was updating. So see the example first the algorithm. So same thing we are doing. You can see the right hand side over here. Over here, there is a column on S which is initiated by S1 equals to 1 and S2 equal to 0. Whereas T will be initiated as T1 equal to 0 and T2 equals to 1. So please make a note of this, that the left hand side GCD, this is the part that we have already discussed. Euclidean algorithm for GCD calculation. But for S and T we have separate two elements present, and for that the algorithm wise, please make a note of the equation that is given over here. S equals to, so remainder part is same as it is already there with us. S, if you observe here, updating S is given by S1 minus Q into S2, and T is given by T1 minus Q into T2. But remember one thing, S1 is initiated as 1, S2 is initiated as 0, whereas T in that case is reversed, 0 and 1. Okay, so the R1 equals to A and R2 equals to B, that part is similar to the previous example. But this S1, S2 are the two variables which we are defining specifically using the extended Euclidean algorithm to find out two more integers S and T which might be related to the GCD of A comma B. Okay, so if this is given the fact, then let's see if we can find out for 161 and 28. So for this particular element, you can see the question, find the S and T. Alright, so the process is very simple. You can observe that we are looking at a scenario where up to this part we have done. Isn't it? The red column, that is what we have solved so far. So the S1 to S, this part is where the new part comes in. Alright, so how we are doing it? Simply we are substituting 1 and 0 as S2, S1 and S2. And for T1, T0, T2 we are updating as 0 and 1. And each and every time we are updating in the same manner with the following trend, that S will be S1 minus Q into S2 and T will be T1 minus Q into T2, keeping the fact that R is already we have defined as R1 minus Q into R2. So based on that we will go on doing it, and you will observe that this part is what we have found out. This is the GCD element. But for S1 we are getting something like minus 1 and S2 we are getting as 6. So considering any such big numbers, any number, we can find out another two numbers which will hold that equation true. So keeping that in mind, if you can solve the next one, is there any doubt over here? It's basically repeating the same thing, the one that we have discussed, except that the rigorous calculation will become a little more. Can you find me the GCD and the S and T for, please make a note of it. I think it is there, here. For a number 527, 341, find the value of S and T using extended Euclidean algorithm. Please do it once again. So the table, hopefully all of you understood, Q, R1, R2, R. So that's already which we already understood. Then we have to add S1, S2, S, T1, T2, T. That's the other 6 column that you have to add. And remember, S1 and S2 should be initiated as 1, 0, and T1 and T2 should be initiated as 0 and 1. I'll just keep. Can you keep the answer over here? I'll give you the table again. GCD of 527, 341. This is the table. I'm keeping it as a reference for all of you to understand. Okay, please make a note of it and finish it off. The values are given by 527 and 341. So your A and B are 527 and 341. Use the extended Euclidean algorithm to find S and T. In the process, you will also find the GCD also, but we are not focused on that. We try to find out the S and T. For the answer. So I'm not doing the whole step. It will be there in the course page. So S will be equals to 2 and T will be minus 3. If you are getting that, and in the process what you got as GCD? 31. Correct. Now what will happen to this case? 0, 45 for that matter. If A and B are 0 and 45, it's very easy. We will get a similar result of 0 and 1. So just one of the example, and same as that of the other one also. If A equal to 17, any one of the elements they are 0. It's very simple. We can get its answer in one line itself. So that's just a condition. Now if we come to modular arithmetic again, we are already aware of it, so we are not going to waste much time on this. We already know that all this process has already been applied to the algorithms which we have come across, so we don't need much difference. But the only difference you can observe that here we are having modular any operator. You can see it's not limited to 26. Unlike to the algorithms where we have considered as modular 26, since we had 26 alphabet, here we are discussing about anything for that matter. So modular mod 25, 12, mod 14 for that matter. Okay, so that's how it is. And again the minus 18 we are looking at, that will be converted to positive. We have already discussed that. We don't need to invest much here. Congruence operator, again if you remember we had discussed already, where we are looking at this 3 equal kind of sign. This is where the congruence thing. So what was congruence? It is that the resultant will be similar. So you can see that 2 congruence of 12, it means 12 mod 10. The output of it, the residual, the remainder is 2. Similarly, you can see that 23 mod 10. That means the remainder is 3. So in that way, this one, these two, if you consider, they are all congruence. They are both congruent because both the cases, the limiting condition, the remainder will be 3 in both the cases. So we can say they are congruent to each other. So that's how it is done. So we have already discussed, so we are not discussing. Only one thing we haven't discussed previously, and that I think I should keep you an understanding, is that this is also, I think mostly we have done. Please keep a note of these 3 properties which come across. Okay, so property is that if it is A plus B mod of n, please make a note of it. You still have some time, don't close everything right now. We have A plus B mod n. Now this is again useful. This is not dealing with small numbers. Suppose A and B are pretty huge numbers and you want to make a mod of it. Okay, the rule is very simple. We have A mod n plus B mod n and whole mod n. You will soon find that when we come across again that Fermat and Euler theorem, we will utilize these properties also, but for the time being please make a note of it. So A plus B mod n can be represented as A mod n plus B mod n. On the other hand, A minus B in the same manner, and A multiplication to B can also be mentioned as A mod n multiplied by B mod n. So you can see the examples given over here. Although it is taken very small numbers 11 and 15, but ideally can be applicable for any big numbers also. Especially this is applicable when the numbers are pretty big. Then we are not in a position to add up them and then take the division of it, so it's very like waste of time for that matter. So these are the properties which we can apply and we can get a very simple result in a very quick time. Okay, remember that we are dealing with numbers only and these properties will help us in finding out that. Alright? Achha, can you quickly, before we end up, can you quickly do this? Can you prove that how this minus 31 is equal to 8? Can anyone please do me and tell me? Or maybe minus 1230 mod of 19. Why it is 5? This is nothing to do with the properties. We have discussed that how the negative numbers are dealt in modular operators. Can you just prove that in your own question answer sheet? Minus 1230 mod of 19. Why the resultant is 5? Can you quickly do me and tell me, or at least let me tell me that how it is 5? Because you have not asked me the question, so I thought I'll ask you the question. So hopefully you have understood, that's why you have not asked the question. Why minus 1230 mod 19 is equal to 5? Can anyone tell me? Because the remainder is negative here. And as I said, we had started off in the discussion that if the negative remainder comes in or the negative quotient comes in, we have to make sure the quotient is increased by 1 and the remainder is subtracted from the modulo value. So that's why it will come as 15. So minus 14 will come to 5. So that's the in-between steps in between. That's why we are not discussing over here. It is hopefully that you have understood that. So that's why the thing is, before we end up, last but not the least, we will see this later. last one before we end up. Multiplicative inverse we are not going to discuss much because we have discussed. Additive inverse, this term you add up. Additive inverse is a process in which it is a plus b which will be equal to 0. It's like we have mentioned the congruence operator, but it means that a plus b divided by mod n, that is the mod value, should give us a resultant which is remainder will be 0. So for example, you can see Z10 we have considered. So what are the additive inverse of this particular set of elements? They will be 0, 0, 9, 1 or 1, 9, 2, 8, 3, 7, 4, 6 and 5, 5. So they are called as additive inverse. We will again use that later. For the time being, since we have not introduced this term before, so I just thought of telling you right now, we will use that later. Alright. So this is all about the first days of our mathematical introduction. We will see that from this point onward how things goes with the groups and set where we are going to apply these conditions on top of it.